All right, thanks everyone for coming out. As I was saying just before I started the video, I'm going to start by reviewing the material that it just explains the basic concept of a quantified categorical statement and reasoning with quantified categorical statements. Then we'll stop the video, we'll do the exercise on just on the parts of a quantified categorical statement. Then we'll go back and talk about inductive syllogisms, or rather inductive generalizations and instantiation syllogisms. Okay, so we're dealing with a certain kind of statement here the first way to get used to it is just to think about examples. So here's some examples from the text. All Canadians are humans. Most physicists are smart. Few teachers are rock climbers. No dogs are cats. Some Americans are doctors. Some adults are not logicians. All of these are what we call quantified categorical statements. They are quantified categorical statements because, just look at the example here. Some adults are not logicians. It's got what we call a quantifier in it. It is a word or phrase that indicates how many. And then it's got two categories in it. And so in this case, the examples are adults and logicians. So the quantified categorical statement describes how many things in one category also belong to another category. So it's quantified, meaning it has a term saying how many. It's categorical because it contains two category terms. And then finally, it's a statement, meaning that it is a bit of language that can be true or false. It's not a question, it's not a command, it's a complete sentence. It makes an assertion about the relationship between two categories. So the first batch of exercises just asks you to identify the basic parts of a quantified categorical statement.
Yay, you were dissecting sentences.
Okay, yes, dissecting sentences. More, and then later arguments, and then we're back to critical thinking. So some of the examples are going to be really simple. In these cases, you're going to have everything's going to be explicit in the sentence and represented by an individual word or phrase. So some Americans are doctors. The quantifier is some. The first category we call the subject term, and that is Americans. Then there's what we call a copula, which is just a form of the verb to be, and almost all of the time it's going to be are. It might be the singular is, but mostly it's just going to be are. And this is just something that couples together the subject term and the predicate term, the two categories. So in this case, the second category is called the predicate term, and that is doctors, right? The only thing you have to worry about here are some tricky cases, because what we're doing is we're standardizing English, which has all sorts of irregularities in it, and creating a more rigorous form. And so if we were in the formal logic class, a whole lot of time would be spent standardizing different kinds of English sentences into standardized sentences that could then be used for formal logic. But here we're just going to do a little bit of standardization just to indicate the range of sentences that can be treated using the kinds of tools that we're talking about. So consider this sentence. 30% of Canadians speak French. So what's the quantifier here?
30%.
30%. That's easy enough. What's the subject term?
Canadians.
Canadians.
Yep.
But we don't have an R, we don't have a copula, and instead of a subject, instead of a predicate term, we've got this verb phrase, speak French. Now you have to remember that categories are always defined by noun phrases. So we want to change the verb phrase here into into a noun phrase so that we can talk about the quantified relationship between two categories. So what we're going to do is we're going to say that the copula is implicit and the predicate term is just people who speak French. And so in general, what we're going to do in this kind of situation is we're going to take this verb phrase and we're going to add people who or things that in front of it to turn it into a noun phrase, right? So we've got some exercises here. The copula can be implicit, and sometimes the predicate must be transformed into a noun phrase. So why don't you, I think I just have 7 quick examples on the sheet I handed out. Take a second to do those, and then we'll start to talk about arguments that use quantified categorical statements. So when we talk about the terms, actually what's going to happen is we're going to wind up breaking those into variables and values, right? And actually, let me take a step back. So in the previous section, we identified what a quantified categorical statement was and looked at its parts. Now we want to bring in some more terminology so that we can start to apply more actually ideas from probability and statistics, right? So when we have a category, let's just take the sentence, 50% of the balls are blue, right? The predicate there, things that are blue, is actually a specific value that can be taken by a variable, which we could label like color, right? Often what happens is our first category identifies a whole population that we want to study, and our second category identifies the values that a certain variable takes, right? So the variable is just a property of individuals in a population that can take many forms, and the values are the different forms the property can take. And for a lot of the examples we're going to be using, because we're drawing a little bit on statistics here, what we want to do is take, we're going to be using the example of balls in an urn, because that's just tradition for statistics. So you can imagine that the balls might have a number of different properties. They might be different sizes, they might be different colors, but so here the variable is color, and the values that variable can take are red and green, right? So here's a sentence that I use in my ethics class when I'm talking about statistics, because we do actually statistics and ethics, funnily enough, because we study eviction. And so here's a statement. It's a quantified categorical statement. 1 in 8 Milwaukee renters experienced a forced move. This is about a study of eviction in Milwaukee a little bit ago. But in any case. So what's our quantifier?
1 in 8.
1 in 8. What is the subject term?
Milwaukee renters.
Yeah. And what's the copula and the predicate term?
The copula is implicit,
Yes.
and the predicate term are people who experienced a forced move.
Right. So 1 in 8 category, Milwaukee renters, are implicit copula. Category, people who experienced a forced move. right? So we can say that Milwaukee renters is a variable F, and people who experienced a forced move is a part of a variable G, right? And then what we would say is the variable Milwaukee renters can take two values, and that's just going to be yes or no. And then people who experienced a forced move takes two values, yes or no, right? So I'm mixing together some ideas from different ways of studying quantified categorical statements, just to give you a variety of tools. But if we were, when we're analyzing some empirical science, this is generally the way I phrase things. Okay, so we want to, in this section, we're concerned with two styles of argument. Previously, I said that when we were doing critical thinking, we would identify various argumentation schemes, right? You had a basic idea, which was to put arguments in standard form with premises and conclusion marked. Argumentation schemes are subtypes of standard form where you have certain kinds of premises and certain kinds of conclusions. So we did argumentation schemes for arguments from authority and arguments by analogy. Now we're going to do two more argumentation schemes: inductive generalization and instantiation syllogism. And the difference between these is essentially where you have a quantified categorical statement. So inductive generalization, broadly speaking, is just reasoning from particulars to a generalization. So you start with statements about particular objects, and you wind up with a quantified categorical statement. Right? Really common example to see here is the generalization that all swans are white. So Europeans, for the longest time, had this idea, a biological generalization: all swans are white. And then they traveled to Australia and they discovered a black swan. So that, a whole bunch of them actually. So that generalization turned out to be false. And ever since then, this has just been used as a standard example of inductive generalization. So this general statement was made by having repeated experiences with individual swans and discovering they are white, right? So these are all just particular experiences. Look, this is a white swan, 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 this is a white swan. So the picture on this slide has clip art of a bunch of swans on the bottom, surrounded by the word, and they're all surrounding the word particulars. Then there's a great big arrow going up to the general statement: all swans are white. And so this is the form of a generalization. The instantiation syllogism is a syllogism that a form of reasoning that goes the other direction. You start with a quantified categorical statement in the premises, and you go to a particular. So you might have a generalization like all swans are white, and then you go to a particular. Odette the swan is probably white. And so here we've got the heading is generalization. Right under it is the generalization itself: all swans are white. Then there's a big arrow pointing down to the word particulars, and there's another clip art swan who is labeled Odette, and the statement is Odette the swan is probably white. Generally, when we are dealing with this reasoning with quantified categorical statements, we are in the realm of induction. Do we remember the difference between induction and deduction?
Fact and validity.
Yeah, it's so validity is the key word. Fact is not one that we. oddly enough, fact just doesn't quite come up in critical thinking. And there are complicated reasons for that. We just talk about statements, and they may be true or false. Deductive arguments are valid, which means that the premises show the conclusion must be true with exact certainty if you assume that the premises are true.
Aren't inductive reasonings like cogent or strong?
Yeah, so rather than talking about when you're in the realm of induction, rather than talking about valid arguments, you talk about strong arguments. Now, technically, an inductive syllogism with a perfectly universal premise, all swans are white, going down to your conclusion, Odette is probably a white swan, that is actually deductive reasoning. And it matches, it is in fact the standard example of deductive reasoning used in the European tradition forever. Socrates, all people are mortal, Socrates is a person, therefore Socrates is mortal. So there is one situation in which the kinds of statements that we're looking at now yield deductive reasonings. But mostly, we're going to be in the realm of induction. And honestly, all that happens when you turn one of these statements deductive is that you dump all of the, you've made the premise really strong, right? You've gone up to from most to all. And so rather than having faulty reasoning now, you just worry about whether or not your premise is actually true. And so for the case of swans, turns out the universal premise is false. So what we want to do to represent an inductive generalization is we're going to have one premise that just lists all of the cases. And technically speaking, I'm getting this from my co-author, Cal Woods. You would actually have it written, you'd want to say case 1, here's a white swan, case 2, here's a white swan, all the way up to case N. But generally what we want to make that more intelligible in English, we're going to say something like, I have examined 57 swans, right? And that's premise 1. We've just got this number of cases. And then premise 2, a certain percent of those cases also had another property, G. So the first cases are all cases of swans. The second list is a bunch of things that are cases of being white, right? And then you draw the conclusion that all swans are white.
I'm wondering if when we use this model for like research purposes, maybe, not sure.
Yeah. So we're going to use this just to standardize existing research, right? And there are formats, if you are actually doing research, if we were scientists, there are certain ways that you're going to present it. We are representing things to ourselves this way in order to understand the underlying logic of it and sort of judge scientific information. The question is whether we are, the goal here is to be a good consumer of scientific generalizations. And in order to do that, we need to understand sort of the logic of how they work. All right. With argumentation schemes like this, you've got the main premises that need to be a part of the argument, and then you've got additional questions that should be asked of any argument that might fit this. And we can think of those as implicit premises for the argument. So the implicit premises here are that the sample is large and that the sampling method yields a representative sample. So the sample is large, the sample is representative. From those two premises, you can get to the conclusion, in this case, it's all swans are white, or you could say roughly 100% of all cases of being a swan is also a case of being white, something like that. But what it comes down to is that whenever we have an inductive generalization, we're going to be asking two questions. Is the sample large enough, and is the sample biased? Let's zoom in on the language of sampling here. We want to talk about a population and a sample. Whenever we're dealing with a generalization, we're making a claim about a whole range of individuals. And so we call that range of individuals the population. Oh. Okay. So the population is the set of individuals that you want to make a generalization about. Yeah.
Oh no, I was just scanning the words.
Oh yeah. Okay. So to return to the example of balls in a jar or an urn, right? The whole urn is the population. The sample is the smaller portion of the population that you actually have knowledge of, right? That you actually measure in some way. So if you're pulling balls from an urn, the sample is the balls you pull out. Okay. So what we want to say, with each argumentation scheme, there is a associated fallacy, right? So a fallacy, the fallacy that we say is associated with inductive generalization is a hasty generalization, right? So a hasty generalization is the fallacy that is committed when one makes an inductive generalization based on a sample that is either small or biased, or both, right? Okay. So the other argumentation scheme that we want to look at is the one that goes the other way. It starts out with a generalization and you go down to a particular. So you start with a generalization. Roughly some percent of cases of F are also G. And then we say case 1 is an F, and then we conclude case 1 is a G. So roughly 100% of all cases of being a swan are cases where you are white. Odette is a swan, therefore Odette is white. Roughly 100% of all cases of being a person are cases of being mortal. Socrates is a person, therefore Socrates is mortal. The trick here is to remember that there is an implicit premise. We want to imagine that our case is typical. So if you have a universal generalization like all, then you're fine. If you have a partial generalization, like say 60% of all, 60% of Canadians speak French, right? Now you need to be sure, if you're picking a random Canadian, that
They speak French.
it's genuinely random, right? And then you can infer that they're likely to speak French if you knew that it was genuinely picked at random, right? But there may be external information. So if I say that roughly 60% of Canadians speak French, Jacques is a Canadian, therefore Jacques speaks French, you want to say that's a 60% chance, but actually there's extra information there, right? That extra information is that this guy is a French name, which actually would want to indicate, would boost your confidence in the generalization. So in general, the idea is that the critical question for an instantiation syllogism is this a typical case? And so there are two. So for any inductive generalization, the two critical questions you have to ask are, is the sample representative, and is the sample large enough? When you are doing the instantiation syllogism, your critical question is whether you are dealing with a typical example. All right, so what I want to do next is give you some tools for deciding whether or not those critical questions are properly answered. So the first thing to think about is the phrase margin of error. And I totally need to redo this slide so that it's more clear. Because right now I'm using some
I've heard of that before. I've heard of that before.
Yeah, actually I'm going to go ahead and change this slide live. So,
Wait, no, come
on. So the margin of error is the range around a sampled value such that we can be 90% sure the real value is in that range. So we are always dealing with a sample and a population, right? Your overall population is, for instance, marbles in a jar. The sample is the marbles that you pulled out.
That's why I remember that from the statement. When I was in high school, we were learning about logistic reasoning, and we had to use margin of error as one of our like terms that we had to learn. And I can't believe I remember it.
It's a useful term to remember. And now that you've heard it in two different contexts, you're more likely to remember it in general.
Yep.
So we want to make a generalization about a huge class of things, but we only know about the sample. We're going to have some number that's true of our sample, and we want to know whether it's also true of the whole population. The margin of error is a range around the number that we got, where we can be 95% sure the range in the actual population is somewhere, the value of the actual population is somewhere in that range. So, if the frequency of red marbles in our sample is 55%, and the margin of error is plus or minus 3%, we can be 95% sure that the actual range is somewhere between, the actual value is somewhere between 52 and 58%, right? Let me fix this again. The actual value is between 52 and 58%. So basically what's going to happen is when someone is throwing statistics at you, they're going to give you a margin of error, right? And so they'll say 45% of people polled approve of Biden's handling of the economy. Margin of error plus or minus 3%. Right? And so what that means is somewhere between 42 and 48% of the real population is going to approve of Biden's handling of the economy, and we can be 95% sure of that. So what happens with margin of error, when you are given a margin of error, it is calculated on the assumption that the sample was genuinely random. Here, let me scooch ahead. Random sample here.
Now that I think about it, it was more than like one area subject that we had to learn about margin of error.
It's an important idea.
I think it was in math.
Yeah.
That was the first one I actually learned.
So, a random sample is a sample in which each member of the population has an equal chance of being in the sample, right? And so when you say there's a plus or minus 3% margin of error, that is assuming that the sample was genuinely random. And so the margin of error is calculated just by knowing the relationship between the size of the population and the size of the sample, and a few other factors, right? So the margin of error covers the mistakes that come up in genuinely random samples. It does not cover mistakes from non-random samples or other problems with data gathering, right? So rather than talking about how to calculate margins of error, I want to show you two problems, two kinds of samples that are have problems on top of the margin of error. This is the self-selected sample and the sample of convenience. A self-selected sample is a sample in which people choose to be in the sample, right? Imagine you're trying to pull balls out of an urn, and instead of just pulling them at random, some balls squirm their way up to the top with their little arms and legs and leap into your hand. That sample is no longer random because it might be that the green balls have bigger arms and they're more likely to come to the surface. Okay, that was silly and you can't picture that. But now think about the example we saw in that the example of that phone-in poll from Fox News. Rather than selecting people randomly from all over America, or even randomly from all over Fox News viewers, it was a sample of people who chose to pick up the phone, call Fox News, and tell them their opinion, right? A self-selected sample overrepresents extreme views when you're doing political polling. In other sorts of circumstances, self-selected samples tend to overrepresent other sorts of extremes. So in, for instance, sex surveys, people with unusual, non-standard sexual habits will be overrepresented in self-selected samples.
Is that because when it comes to like political polls, like more people who are extreme want to get their voices heard than people who aren't?
Yeah. You're getting people who are motivated for one reason or another, and that's going to throw off your sample in one way or another.
Especially with the Fox News or CNN, because all those people are overly biased.
Right. So the interesting thing about the Fox News example is that sample would be biased even if you were just trying to make a generalization to all Fox News viewers rather than all of the United States. Because even within the category of Fox News viewers, people who respond to phone-in polls are going to be more extreme in their beliefs than just the ordinary Fox News viewer, who in turn is more extreme in their beliefs than the average American. Yeah?
Quick question, is there a review sheet for the next test that's coming up, or?
You know, there isn't, and I need to make that and post it.
Okay.
So
I was concerned about that.
Yeah. There'll be a review sheet and a practice test and all of that stuff.
I'm going to email you and remind you.
Yeah, sure. Yeah. Okay.
How we for time?
2 minutes.
Let me just hit the other kind of sample that we want to be aware of, and this is the sample of convenience. So this is a sample of individuals that happen to be accessible to the researcher. And a standard example to use here is psychological surveys. Most psychological surveys are conducted on freshmen in Psych 101 classes. And they're conducted on freshmen in Psych 101 classes because those people are available. They're convenient. but they are not representative of the overall population. They are 18 to 24. They tend to be wealthier. They tend to be better educated and in the process of becoming even more educated than the population of the US, let alone the world. Another common sample of convenience now is actually Amazon's Mechanical Turk, where Amazon will pay people to take surveys. If you do English language surveys, actually what you get is a lot of English speakers in India, because there's a population there where a lot of people speak English, so they can conduct surveys in English, but because of the difference in the value of the currency and overall poverty rates, it becomes profitable to just take surveys for a living. But again, it's still another kind of bias, right? You're gonna be looking at a different kind of population than a genuinely random population. All right, so we're out of time. I'm going to stop this video here. I'm going to try and supplement this later with more things to put online.